Hey, welcome back to Math with Patrick. Today is May 31st, and we're solving problem number 151 from the Daily Epsilon calendar. Let's get into it. All right, so the answer should be 31. So it looks like once we figure out what this value is here for z, we can plug it into this quite long sum. Looks like there are, 31 terms in here. And then once we add it all up, we should get the number 31. So this is just a quadratic, and I think the easiest way to solve it is probably just the quadratic formula. I don't really recognize it as something that's like easily factorable, so I'm just going to quadratic formula this guy. I'll say that z is equal to plus or minus negative b. B is this coefficient on the middle term. There isn't one, so it's actually just 1. So negative b, whoa, that should have been negative b here, plus or minus a square root of b squared, so that's just 1, minus 4ac. So a is right here, c is right here. Basically, all of my coefficients are just 1. So 4 times a times c is just going to be 4. And then all over 2a. And again, a is right here. A is just 1. So 2a is going to be 2. So what I'm noticing here is with this like negative discriminant in this quadratic, I'm going to get some complex roots. Essentially, there is no like real number that can make this equation true. And we kind of have to dip into complex numbers to find some solutions here. So z is going to be equal to, how about I'll just go, I'll write it as two different answers because this plus and minus sign you can kind of split up. So negative 1 plus negative root 3 over 2, or it's going to be equal to negative 1 minus root 3 over 2. And how about let's actually convert these into complex numbers. Any time you have a negative square root, you can remove this negative sign by calling it the letter or the number I. It's like the complex unit. It's just defined as when you square it, you get negative 1, or maybe when you square root negative 1, you get I. And taking this definition right here, I could rewrite the inside as I squared, because that's the negative sign, times 2 squared. And then when I square root this, I get 2i. So anytime you have a negative sign on the inside of a square root, you can, if you want, take that negative sign out as the number I. So I have two solutions for z. Z is either equal to negative 1 plus I root 3 over 2, or it's going to be the conjugate, essentially, just the same thing, but with a negative sign instead of this plus sign right here. All right. And supposedly, if I follow this like rule, this sum, I should get the number 31. And what I think is going to happen is that all of these are, I think, just the number 1. And so first, let's prove that how about z cubed is 1. And then I'll double check and show that there's actually 31 ones all being added up here. One way to do powers of complex numbers is just to multiply them. So I could do like negative 1 plus I root 3 over 2 and then cube it. And so I'd have to like do this multiplication like 3 times over because that's what it means to cube things. Though for any time that I'm doing these high powers of complex numbers, I do like to reference de Moivre's theorem. It's a French guy back in the day, mathematician, who basically figured out, or at least proved in a theorem, that multiplying complex numbers essentially give you rotations around the complex plane. So first, we should graph these complex numbers. I will have a real axis here, and then an imaginary axis here. And when I'm graphing these two complex numbers, I should do the real part left to right. So it looks like negative 1/2. I'll make some tick marks here for myself. I'll call this 1 and negative 1. And actually, both of the real components of both of these complex numbers are negative 1/2. So I'll go back to negative 1/2 for both of them. And then for this first complex number, I'm going to go up because of this plus sign. I'm going to go up root 3 over 2 units. That's around like 0.7-ish. So essentially a little bit more than 1/2. And so when I draw my tick marks here, I'm just going to make sure that my point is going to be a little bit higher than 1/2 in the imaginary direction. And the other complex number should go -1/2 backwards and then down here. There we go. So here are where my complex numbers are on the complex plane. And whenever you do powers of complex numbers, you can just add this angle to itself over and over and over again until you kind of reach the end, I guess. So this complex number here, when I raise it to the power of 3, I'm going to do 3 rotations of this amount, because the first rotation, the first power, will get me exactly right here to the complex number on the plane. And this right here, I guess I should show that this is 120 degrees because it isn't immediately obvious. If we zoom in on, say, a right triangle right here, I'd like to show that this is a 30, 60, 90 triangle. We can kind of redraw the triangle here. It's going to have a distance of 1/2 on the bottom there. It's going to have a distance of √3/2 right here. That's just kind of directly coming from the numbers in the complex number. And if you do the Pythagorean theorem on this guy, you would just get a 1 as the hypotenuse. And this setup essentially is just, it's a 30, 60, 90 triangle. Maybe you can think about kind of mirroring it right here. And these 1/2s form a 1 together, and we've essentially formed an equilateral triangle. There's 60 degrees in all 3 corners here, here, and here. And so when we cut it in half, it's definitely a 30, 60, 90 triangle. So what that does is that tells me that this angle right here is exactly 120 degrees. And so when I kind of follow the ideas of de Moivre's theorem, and I do rotations around the complex plane to multiply complex numbers, my first power will land exactly at 120 degrees. My second power will land at exactly 240 degrees. And then my third power is going to land me right back there at the real axis. And so I do know that when I cube this complex number, I'm going to get a purely real number. And there's another part of de Moivre's theorem that tells you how big that real number is going to be. And essentially, any time that you multiply a complex number by itself, you should multiply the magnitudes or the moduli, the moduluses together. That's just this distance here away from the origin. And so since that distance is 1, every time I do a power of this complex number, the modulus is just going to be 1 times 1 times 1 times 1. It'll just be 1 the whole way through. So knowing some facts about like complex numbers and rotations, I'm able to say that z cubed is just going to be 1. And it doesn't matter what z either, because if I think about this rotation here, the first rotation would be 240 degrees. Then the next rotation would bring me here, which is whatever, 240 to 480 degrees. And then the third rotation will bring me back to the real axis. And that demonstrates that cubing this complex number, I also get a real number. And this one also has a modulus of 1. Its distance away from the origin is just 1. And so whenever I do powers of that number, I'm not going to really change its distance away from the origin. I'm just kind of cycling it around the complex plane. So it doesn't matter what z I choose. And I think I'll kind of demonstrate that by just saying that this z cubed is equal to 1, and also this z cubed is still just equal to 1. And that does mean that any power of z where the power is a multiple of 3 is also just going to be another 1, because we could rewrite this as like z cubed and then squared, and we know that z cubed is 1, and then 1 to any power is still just 1. So all of these powers, all the way up until, any multiple of 3, but specifically up until 90, these are all just going to be 1. Now, I should just show that there are 31 1s in here, because it's not quite obvious how many there are. We can just kind of see how we're counting down by threes. And so we have the numbers like 90, 87, 84, all the way down to 3. And if we divide each of them by 3, we can kind of see that we have 30, 29, 28, all the way down to 1. And clearly there's 30 numbers here. So that means that there are 30 ones in this sum. And then finally adding that last one gives us 31 for today. So if you want to do it on your own, you could totally try expanding this out, multiplying all three things. You are going to get the number 1. And I just didn't feel like doing all of that complex number arithmetic because that felt a little tedious. But ultimately, the answer is 31 for today. And I'm going to call it. We're all done. So thanks for coming along. And I'll see you in June. Alrighty. Bye-bye.